really the real fans of cosmology here. And we have the third lecture by Sergei Ketov.
Okay, thank you very much. Okay, so thank you for coming here. This is the third and last lecture of my mini course. There will be also the colloquium on February 20th. It will be on much more qualitative level, more general setup, but it is about the same things. So first, I would like to summarize what we discussed in the first two lectures about dark energy, dark matter, and inflation. How to say? Well, you know, there are two levels of knowledge, on a description level and on a understanding level. So on a description, well, maybe this watch is a good example. Description level means you have some arrows, you have the frame, you have the bracelet, but the mechanism is inside and it is pretty sophisticated, okay? So if we talk about the dark energy and dark matter, in terms of dark energy, I offered you only description level of understanding as a small positive cosmological constant. It doesn't tell you what is the nature of dark energy. In terms of dark matter, I also offered you only description level of dark matter as a CDM, yeah, called dark matter, which doesn't interact electromagnetically, not baryonic, and has a as a stable or metastable with a lifetime beyond the age of the universe. But as regards inflation, I offered you both. I offered you the description level as a cosmological paradigm, and I offered you specific, detailed, and highly successful mechanism of inflation, which is a Starobinsky inflation. The main point of Starobinsky inflation is a gravitational origin of inflation. And because of success of Starobinsky inflation, I want to build up more on that and offer you gravitational origin of dark matter too. Not as a separate story, but as a continuation of the story which I started yesterday. So the topic of today is will be about black holes, primordial black holes, and as dark matter and induced gravity waves. Okay, so again, as an introduction, I will remind you what are black holes from a mathematical point of view and what we observe. So let me start general relativity. Yeah? General relativity, Einstein's theory has solutions. So right after discovery, right after proposal of Einstein of general relativity, people started to search for solutions to Einstein equations. And in particular, if you have the vacuum solutions, which is Ricci flat, yeah, this is the second order differential equations for the metric. So you can find a solution, yeah, which is this one, which is known as the Schwarzschild solution. What is remarkable about that? You have here these particular factors, okay? This is in a spherical coordinates in space and by using the spherical symmetry. And you hear here something remarkable, yeah? You have this factor, so you have what is called the gravitational radius or Schwarzschild radius of a body of mass m. You also have gravitational radius like a temperature and pressure. I recommend you to check your gravitational radius. You know your mass, okay? You may also, and so this is in full with fundamental constants. And this fact is quite remarkable because it breaks space-time into causally disconnected pieces. So because there is a horizon, okay? And horizon appears, for example, when the size of the body is less than gravitational radius. This is a black hole. Okay? So this is a condition. So well, you can check also if you wish to become black hole, yeah, you know your radius, so you can calculate what is your density should be. This is what I usually recommend to my students to do this homework. It's quite useful. And okay, so this is not the only solution to Einstein equations, or because there is a general statement in classical general relativity that black holes are essentially specified only by three parameters, which is a mass, electric charge and angular momentum. So this is called no-hair theorem. And so there are more general solutions, which I briefly review just for completeness and for comparison. Okay, so for example, you can consider the Einstein-Maxwell theory, which is a standard equation of motion with the energy momentum tensor of electric field. Then you find what is called Reinsner and Nordström solution, exact solution to this equation, which is given here. So it can describe black holes with electric charge. Q is electric charge, okay? So the distinguished feature of this is the existence of two horizons. I will not go into details because in astronomy, we have never observed any star or black holes with electric charge, okay? But still, there is such a possibility. Okay, and most general black hole, which has both angular momentum charge, electric charge, and mass, is known as the Kerr-Newman solution. And this is how it looks like, a bit complicated, but this is, I don't want to go into details, but I just want to tell you that most of astrophysical objects have angular momentum, but don't have charge. So usually, in astrophysics, they deal with Kerr solution. So just take Q0 here, okay? So that's what is written here. So in my in what follows, I will mostly consider just Schwarzschild solutions by some reason, which I will let you know. But you should keep in mind Kerr solution too. Okay, so but this is classical picture. Yeah? Classical picture basically tells you that anything which falls inside black holes never come back, and but classical black hole doesn't radiate, so it is usual stuff. Yeah, but it's just, if you go to quantum theory, there is it's not true. There is such a thing which is known as Hawking radiation, which basically, if you take a black hole as a black body radiation, you can calculate quantum effects semi-classically, and this was why Hawking is famous for. Yeah, so he found that actually black hole has a temperature, and this temperature is inverse to its mass. So if you reconstruct back all fundamental constants, it's like this. Yeah, so this is quantum effect. It's proportional to h bar. If h bar 0, there is no classical correspondence. Yeah, you can. It's also advisable to rewrite it in terms of mass of the sun. So you see, if you just take a mass equal to mass of the sun, this is temperature negligible. So it is kind of almost nothing. Yeah, but if suppose mass is very small, then it can become significant business. Okay, so this is nothing but quantum mechanics principle. Yeah, that's, you know, Tulin effect in quantum mechanics. So I will just take it. Yeah, there is a semi-classical derivation in textbook of this formula. This will play a role in what follows. Huh? It has nothing to do with CMB. It is just a Hawking radiation of. No, CMB is electromagnetic radiation. It is a relic radiation. When radiation. I'm not talking about the origin at the moment. I will come to this. I'm just telling you that if you have the black hole, it has to radiate, and it has such a temperature. Okay, this is there is nothing about origin at the moment. It's just a fact which you derive from systematically, but in semi-classical approximation. That means you shouldn't trust this formula for very small masses, but like a particle mass. Yeah, but semi-classically, this is well-established result. And okay, so let's continue. Actually, this also can be related to the thermodynamics, of course. So, for example, if you use Hawking radiation, you can easily calculate this Wittgenstein-Hawking entropy, which is also classical, famous results about the entropy of black holes. But the difference is, or the main issue is that we don't know microscopic derivation of this entropy. We have only macroscopic. So this is a big issue, how to derive it macroscopically, and the reason is because we don't know fundamental degrees of freedom for black hole. Good, so this I will probably not go there, so I just want to mention you that this is directly related with Hawking radiation. Okay, so, but what are the puzzles today? When I was a student, I remember some of my teachers, not good teachers maybe, they were telling that the black hole, Einstein is wrong, black hole doesn't exist because we don't see them. If you know the MGU rector, he was Logunov, was just doing that. So, well, if you don't see it, yeah, you have some reasons, but now we have established that black hole exists, okay? But there are more puzzles, namely, first of all, what's your question? What is the origin of black hole? Okay, so if you go to textbooks in astrophysics, yeah, they will tell you that black hole arises at the end of the star evolution when the nuclear finished. Yeah, star exists because the nuclear expansion compensated by the gravitational attraction. So during this thermonuclear process, the star exists, so we exist. Okay, but when the fuel exhausted, then it explodes, and there are only two possibilities: either it goes to the white dwarf or it goes to the black hole. And it depends upon you can calculate this, and there is a so-called Chladni-Seker limit, which is about 2 solar masses. So this means if the star is more than 2 solar masses, it becomes black hole. If it is less, then it becomes white dwarf. So it is astrophysical black holes and the standard textbook stuff, but it can be questions. So where I'm going to go. Another issue is that we have in our universe so-called supermassive black holes, which have huge masses. So the question arises how they could be how they can exist, because how one can accumulate such a huge masses, which is about 10 to 10 of solar mass. What is procedure in the universe? So this is also big open issue. Okay. Another point is that if you follow strictly the astrophysical origin of black holes, then they shouldn't appear in the very early universe, yeah, because they appear after the star exhausts his nuclear fuel. But if you look deep into the space, how we can look with the Hubble or with the James Webb telescope, then we discover that the black holes exist already in the first giga-year of the universe. So it also needs some explanation. So there is an idea alternative to the astrophysical black holes that perhaps black holes might appear before any astrophysical object existed. Yeah, such black holes are called primordial black holes. Okay, and you may ask what could be the driver of such thing, and inflation is a natural idea for that, because inflation, as I told you, is a huge accelerator of everything, so it can generate in principle perturbations of any size, and in particular may also generate a black hole. So this is where I'm going. Okay, so what are primordial black holes? I just told you, yeah. Even though we don't have a proof yet that they exist, yeah. The most immediate proof would be if somebody will discover a black hole less than 2 solar masses. This is a proof, because astrophysical black holes forbid it. Okay. So this idea actually was put forward a long time ago. It was put first by Zeldovich and Novikov in around 1967. Then it was proposed by Hawking and later developed by Hawking and Carr around 1973. However, at that time it didn't attract much attention, because not to mention that nobody saw black holes or whatever, so it was just an idea. Okay, another issue which immediately comes out, suppose they were produced, what is the basic estimate for their mass and time, yeah, a lifetime? So we can easily do it. For example, we can just take early universe and assume that radius of black hole is about just h, yeah, which is h minus 1. So you can easily calculate the projected mass, which will depend upon the early time, like this. Okay, so just to give estimate, yeah, if you take a Planck time, of course you get a Planck mass, yeah. But if you take a 1 second here, you get something close to the supermassive black holes. So this is sounds interesting, yeah. Okay. So let's go ahead with that. So since black holes evaporate, primordial black holes will also evaporate, yeah, right after when thermalization quickly happens. So we can easily calculate the lifetime of black hole. So we have a Hawking temperature. I can put it in this way. Yeah, and we from here you can easily calculate the lifetime from the Stefan-Boltzmann law. Okay, you know the dm over dt is proportional to the force power of temperature. Okay, and you will find out by integrating this equation that lifetime of black hole is proportional to the cube of mass. So this is a formula. So you can put it in this way. So this formula on the one side is relaxing. I mean, not dangerous for us, because if you put m as a mass of sun, you will get much more time as a age of our universe. Don't worry. Yeah? But if the mass is small, then this becomes pretty small too. So, for example, you can take the age of our universe, which is 10 to 10 years, and see what kind of mass here arises. You will get a bound of 10 to 15 gram. So it means if you, by using Hawking radiation, if the mass of primordial black hole is less than 10 to 15 gram, it will completely evaporate by now. But if it is larger, it will be present today. So this primordial black holes will be present in our universe if their masses are beyond 10 to 15 gram. Okay, good. So you can put it also into seconds. So this means it is about 10 to minus 3 seconds. So this means, for example, during inflation, yeah? Remember, inflation is 10 to minus 36 to 10 to minus 32 seconds. So during inflation, you can generate quite sizable, I mean, you can generate black holes in principle, yeah? I don't go into the details here. I just first estimate which can survive until today. Good. So, as I said before, if you want to really proceed with anything on the level of understanding, yeah, on the more fundamental level, you have to get a mechanism first. Mechanism, how this is, how this works. Then you can understand the time. Okay, so the mechanism is very important. Without mechanisms, one can do very little, just general estimates. Okay, so I gave you a hint at the end of my yesterday's lectures. What could be the mechanism for creation of primordial black holes? Again, I want to capitalize on the success of Starobinsky inflation. So I want to use Starobinsky inflation as a how it's called, a trailer or the kind of driver, yeah, of inflation by generalizing it. In the pure Starobinsky inflation, we don't have such a situation. And when I look in the spectrum, yeah, of scalar perturbations, I gave you this formula, okay, which is valid in the slow roll approximation. And you see here, what is remarkable here, this is just a constant, this is a Hubble, yeah, and here is epsilon. Epsilon is a V prime over V, remember, yeah, it's slow roll parameter. So for CMB perturbations, this has a particular, has a particular scale, 10 to minus 2, okay? But the idea is, okay, if I can arrange epsilon to be very small, then I can get a very high peak in the power spectrum of scalar perturbation. This means I can generate very large perturbation. And since it's a very large density perturbation, then after inflation, it can collapse into the black hole. This is an idea. Okay, so this means I have to arrange another regime, not what is called slow roll approximations, but ultra slow roll approximation where epsilon becomes very small. I want to emphasize that this regime will be very different from slow roll. It's not a part of slow roll, it will be different because we ignore different terms in the exact equations of motion. Okay. Another important issue is that at the scales below inflation, by the way, Starobinsky gave us a scale of inflation, which is about 10 to 13 GeV. Yeah? So at the scales below inflation, not very low scale, but below inflation, say order of magnitude or less, there is no experimental constraints. So it is just such peak is possible. It's not forbidden by observation. Go beyond, we cannot, because this is I told you, there is a bound of Hubble scale, so physics above that doesn't make sense in discussing our universe. So usually these people discuss it in the context of scalar tensor gravity. So they just invent some potential, and to generate ultra slow rho, they just invent a new inflection point in the potential, which can generate, basically epsilon becomes very small. This is the idea. But this is by hand. I want to use gravity, yeah.
Yeah, so my question, but this, the power spectrum is known, it's measured, right? So
CMB measured only, in the limited scale.
Which one that would be the...
At below lowest scale, it's not measured. CMB is, I told you, it's just a window, small window for power spectrum. It doesn't describe all. I skip this, trying to reconstruct this full. It's impossible from CMB. CMB is just a small window. So it doesn't describe all power spectrum, doesn't describe also all potential. So I will show you a slide which will be very clear in a moment.
So you expect this like high peak at smaller scale?
At smaller scale, yeah. Which scale, it depends. It depends what we can do. So it's the approach which I advocate, yeah. There will be limits. I will show you the limits, what you can do, what you cannot. I just making the stage. Okay, so about your question. Exactly. So let us put here the scale, put here the spectrum of scalar perturbations, okay? CMB is here. CMB is here. And its value is about 10 to minus 9. This is what we observe. So if you can generate at lower scale the peak, this means you generate a large perturbation. Large perturbation can collapse into the black hole. This is the idea. The question is, of course, if you do it in terms of potential, you have a free hand. But if you do it in gravity side, it will be highly constrained, and it's precisely how Starobinsky was able to get his famous potential, just by exploiting gravity. And that's what I'm going to do. So you can also estimate how large this peak has to be to generate black hole. This is not difficult to estimate. It has to be 7 orders of magnitude above CMB scale. So this is what we want to get. Like I remember, first I wrote you some qualitative potential for inflation, and then I showed you how to derive it. Here I just showed you what we want physically, and now I want to show you how we can derive it. Okay. Well, this comes from, of course, this is, you say, purely theoretical, but it is not, because now, you know, we have the, yeah, so that's what we want. Yeah. Wait. Will be answered in a few slides, this question. So I'm just telling you what we want to get. And the question is, can we get it? And if what we get, we get. Yeah, and then we compare with LIGO, it will come. It will come. Okay, of course, once you have, can generate primordial black hole, suppose, I will describe your mechanism, then we can ask how, if they be beyond 10 to 15 gram, then they can be dark matter, because they exist in our universe then. So the natural proposal immediately after idea of PBH is that PBH is dark matter. This is not a particle dark matter. It is a black hole dark matter. And I told you, yeah, 25 years of search for particle dark matter failed. It doesn't mean that it is so impossible, but it tells you maybe there is something else. So let us try this, explore this opportunity. Yes.
On precisely that point, in order for primordial black holes to be dark matter, of course, as you said, they must have the right mass, but there must also be the right quantity of them.
Precisely.
Because we have dark matter almost, we know the spatial distribution of dark matter, and we know there's lots of it in the galaxies. How do we know that these black holes are produced in exactly the right...
Precisely. Next slide. Thank you. I love your questions, because they just directing and always to the next. Very good. That's what I'm happy about that. Of course, well, about specific distribution of dark matter, this is too hard question. It has specific distribution, but in the first place, we have to generate abundance of dark matter because we know it from cosmic pies. Okay, so this is precisely, there is a formula for that. So of course it goes under some assumption. So this is a contribution of primordial black holes into the budget of the universe. Yeah, we know this. Yeah, this 25% or scaled in the with normalization it's 0.11. So we have to get these numbers, and if it is whole dark matter, it can be part dark matter. Okay, so but there is a bound from the above. So what is here? So it has to be inversely proportional to the mass and -1/2. Fine. So this is bound for the dark matter. So, so if you want 100% dark matter, this should be 1. If it okay, this is how many effective degrees of freedom of species in our universe, which is basically standard model. So usually this G star is something like 100. Yeah, 106 for standard model. This is just numerical factor, and the most important factor here is beta when we assume the Gaussian distributions of perturbations. And this is what is written here, is so-called Press-Schechter formalism from astrophysics, which allows you to calculate this and give you a formula for beta as long as you know the power spectrum. So if you know power spectrum, you get this sigma. Sigma comes into this Gaussian distribution, and the only parameter you don't know is this crucial delta. Yeah, but delta is should be around from 1/3 to 1 second. Okay, so this gives you way to calculate as long as you know the power spectrum. But power spectrum is delivered from specific mechanism. I will give you mechanism. I can calculate the power spectrum. I can calculate this. That's where I'm going. Okay, just wait. Good. So, what is the intermediate conclusion for the first half of my talk? Black holes exist due to LIGO and, for example, due to Einstein cosmology telescope. Okay, they were predicted by 100 years ago, but discovered very recently. Okay. So, for example, in the center of our galaxy, we believe there is a supermassive black hole known as Sagittarius A star. Okay, so black holes are ideal objects to study the bridge or connections between macro and micro physics, as well as inflation. We just briefly discussed it. We know that they radiate and evaporate, and so they have a finite lifetime. This is just nails, okay? Not under discussion, established fact. So primordial black holes may exist. They are of a viable alternative to astrophysical black holes, and may be a part of whole dark matter. If you want to investigate it in details, we have to offer mechanism of primordial black holes production. I will offer that. And the next question, how I can check it, how I can test this model, how I can get some observable stuff from that. I will argue that it's possible from the induced gravity waves. Primordial black holes' origin was also a very violent event. It resulted in gravity waves. They may be observed. They are different from inflationary gravitational waves. Inflation resulted in gravity wave R, yeah? But primordial black hole production after inflation results in other gravitational waves, which can be calculated, and what I'm going to do. So this is a plan for the second part of my talk. This will be perhaps the most important scene. Okay, so about dark matter. If you go to the literature, suppose you want to study dark matter, you may be very disappointed if you go to the literature, because there are hundreds of dark matter models. You can do your own invent your own particle, add it to, and build something. Say it's stable, it is electromagnetically not interact, and you can build your own theory, okay? But this is not what we want. We want something more fun, spectacular. And most perhaps important message is that all this, it's not all, by the way, it's just all mostly particle dark matter. And despite direct, indirect, and searches which I briefly discussed and will discuss in the colloquium, nothing was found. So maybe dark matter is non-particle type, and primordial black holes is a good candidate for that. So this is for theoreticians, this is an obvious scene. Jump up and study. Okay, but again, if you want to really study it, you need a mechanism. Okay, so about LIGO. What LIGO tells us? LIGO tells us two things: that black holes exist because they observed gravity waves coming from the merger of black holes, and the only thing they were able to calculate is masses of these black holes. They're written here. So LIGO masses in terms of solar mass is between from 10 to 60 or 70 solar masses. These are pretty big black holes. Of course, if they were small, you wouldn't detect gravity waves. Okay. Unfortunately, from mergers of black hole, you cannot extract information how they were originated. It's like, you know, if you destroy, if your house burnt, you don't know how it was built. So this is a problem. But you can calculate masses. So just remember that LIGO masses are about dozens of solar mass, yeah, just for orientation. Okay, so this is, as I told you, yeah, if you have the spectrum of specific spectrum of power perturbations, of power spectrum, like the one which I showed you here, yeah, you can actually calculate what the mass of black holes will be produced out of the gravitational collapse of this peak. So I just tell you the answer. There are several equations for that. Perhaps the one which I'm going to use is this one. So if you know specific spectrum, then you know this epsilon, this is in terms of E-folds, so you can calculate the mass. That's the formula I'm going to use. So it was obtained actually in IPMU some time ago. So what is important of this formula? So this is actually sub-leading term. The most important is this delta n, because you have exponential here. So on the one side, if you want to maximize the mass of primordial black hole, you have to maximize this. But it has to be consistent with inflation. So what happens actually, that if you increase this, the scalar tilting is decreasing and goes out of the observational window. So it means there is an upper limit on the possible mass you can produce, okay, by using the procedure which I described. If you go it small, then the mass will go down and it may become less than 10 to 15, then no use, okay, for dark matter today. So this puts limitations on what you can do, and I just announce first the result and then give you the details. So what will happen if you do it in terms of Starobinsky inflation? Then you discover that possible masses of PBH produced through this peak, through the arranged peak, are between 10 to 17 and 10 to 21 gram. This is above 10 to 15, okay, on the one side, but not very far. It's called asteroid size. Asteroids have similar mass, but the size of such black holes is subatomic. So you shouldn't worry if some of them are inside your body, because it's physically totally acceptable. which looks like I'm telling you something totally impossible. It's not. Okay, good. So how about details? So most of people use the just potential to generate peak or ultra slow row. But as I told you yesterday, it's better to do it on the modified gravity side, because modified gravity side exploits general covariance, it has many limitations. So I'm going to use not a scalar tensor picture or quintessence picture. I'm going to use modified gravity or FR gravity, where I is a scalar, as a Ricci scalar. Yeah. So I remind you, yeah, that they are due to each other. They are equivalent. Okay. So this is a modified gravity, FR gravity, and this is scalar tensor gravity. Just two pictures related by dual transformations. Coupling constants are inverse to each other. This is exactly like in string theory. Okay, so, but it's the same physics. How we come to this model? We want Stravinsky inflation. Stravinsky inflation is essentially governed by this term. We want low energy Newtonian limit. So it should, by small curvatures, it should reduce to standard Einstein. Actually, such problems already appeared some time ago when people tried to describe just dark energy. That not in terms of cosmological constant, but in terms of the effective scalar or in terms of particular function. This is non-trivial business because you have to avoid ghosts. You have to several physical conditions. Actually, there's a whole list of them. So this was proposed for dark energy a long time ago. So it's very difficult to find a function which will simultaneously describe all these things. So we just modified this function and changed the scale. And it is elementary function. Okay, so this has just some shape parameters like G, B. Okay, this is a so-called ABS function, which is well, you see, if your I is 0, then this is all reduces to 1, for example. Yeah, this is some possible corrections, and this is so it introduces a new scale, which is here R0. So this scale, in our case, will play the role of PBH scale. So in addition to the inflationary scale, which is M, we introduce another scale for PBH production, which is R0, and propose this function, which satisfies all formal physical constraints. The statement is that this will be, first of all, it will be consistent with inflation, and also it will be consistent. It will be generate enough. We will generate primordial black holes. So what I want to say here, before I go, yeah, what is the basic physical idea? In terms of potential, I told you, you should generate some new inflection point. And here, the general idea is like for dark energy, we want double inflation. I told you, yes, that inflation requires plateau in potential. So we want two plateaus, one for inflation, another for PBH production, and in between this ultra slow roll phase, which is equivalent to the new inflection point in the potential. So I will show you the pictures, because to generate potential, next it comes to numerical calculations. I cannot write you explicit formulas anymore, but I will give you profiles, because everything is explicit here, okay? So you just make a duality transform, you calculate the potential, you calculate slow roll parameters, you calculate the mass, you calculate Hubble function. This is all can be done with Mathematica, okay? And that's what we did. I just show you the result. So, but before I go to the result, I just want to show you what are the targets. So the target was to generate a large peak in the power spectrum at smaller scales, which is large enough, okay? It has to be consistent with CMB, so to generate the, to fill out this bound. It has to get PBH masses beyond 10 to 15. And this leads to restriction, and to this also to the result. So this is completely classical. One can also show that quantum loop corrections are negligible, despite claims in the literature, but this is for experts. Okay, so I just show you the results of such numerical calculations. So what is, so for example, you see what happens that in the Starobinsky case, due to R squared, you have infinite plateau, but this is violated by any high order terms. Once you add, because they're definitely there, but they are subleading. So once you add them, plateau is no longer infinite and goes either up or down. So what is important here is that this is the potential, okay, in terms of inflaton, which is a scalar physical mode here. So this is inflation, okay, and there is another plateau at lower scales. So we just concentrate. If I take a zoom of this, yeah, you see this extra plateau, and this extra plateau is, if you feel, the second inflation. But between there is a ultra slow row phase. So this is a dynamics of phi. And here again, you see the Hubble function has two plateaux. That's why it's good to call it double inflation scenario. Also, if you look at the slow row parameters, you see indeed epsilon drops significantly, yeah? Many orders of magnitude. So this generates the peak in the power spectrum. But there is a second slow row parameter, eta, which is no longer slow row. You see it's slow row here and here, but not here. This is a manifestation of the ultra slow row phase where slow row conditions are broken. And this translates into the power spectrum, which gives you a peak at lower scales after inflation. You may say, oh, I should perhaps use the exact formalism, so-called Mukhanov-Sasaki equation, but actually it turns out that our approximation Mukhanov-Sasaki give essentially the same results. So not an issue. Okay, so then the question is, okay, fine, we have a model, we have a mechanism. The legitimate question is how it can be checked by future observations or maybe ruled out, okay? So then we need some kind of observational consequences of this. But the most straightforward observational consequence of PBH production is the induced gravity waves. Because like inflation, PBH production is also very violent situation. So it resulted in gravity waves. Question: how to calculate this gravity wave? So and whether they can be observed. Well, you see, this is it's impossible to solve equations exactly, but you can relate density perturbations and scalar perturbation, tensor perturbations if you go to the second order of perturbation theory. So in the first order, they don't see each other. That's what I always was referring to, the first order in perturbations. You have scalar perturbation, tensor perturbation, but in linear order, it's just a sum, naive sum up. But if you go to the second order, they become coupled. So the scalar perturbations affect tensor perturbations. So this is a way how to calculate the so-called PBH-induced gravity waves. I give you the answer. These calculations were done in Europe, in Geneva, and also in Tokyo. Two groups, they get the same results. And in the second order, the contribution of gravity waves is just, you see, it's just the second order in the power spectrum. It's given by this equation. So if you know the perturbations, you calculate this integral and you get the how much gravity waves are produced. And since if you have a mechanism, yeah, you know this PG, so you can calculate. So what happens in our model if I just put this, because we have this, yeah, we can calculate this. So the answer is the following. Well, this is just technicalities. So we find that contribution, roughly speaking, we have more exact formulas, more precise formulas. The contribution of gravity waves to omega is about 10 to minus 6 of square of scalar perturbations. And we also have frequencies of such gravity waves, which are in this range. Yeah, since you have a mass, this, by the way, applies to all gravity waves, but induced gravity waves. But since we have specific masses, asteroid sites, we can get a frequency. So our prediction is 10 to minus 3 hertz for these gravity waves. Then you should go to the people who doing gravitational wave astronomy and ask them what they know about that, what they observe in our universe. They told you, oh, we observe something interesting, which is known as a nanograph. Nanograph is a collaboration that we are measuring, observing, targeting gravitational waves over the last 15 years. They released, I think, last year or recently, the summary of the observations. They discovered gravity waves in this region. That's why I call nano. Yeah, it's a nanohertz region. We don't know the origin of these gravity waves, but there are speculations in literature that these are gravity waves induced by PBH. If it will be proven, then it is another indirect proof of PBH existence. But our prediction is different. You see, it's not nanohertz; it is millihertz. So the question whether there are other projects which can target a millihertz range of gravity waves. The question is, the answer is yes. Namely, if there are such projects in the under construction, I just mentioned 4 of them, which is famous LISA project. This is a European project. There are 2 Chinese projects, which is Tianqin and Taiji, and there is a Japanese project, DeSaigo. All of them are, unlike LIGO, which is a ground-based gravitational interferometer. These are space-based gravitational interferometer, which are under construction. For example, LISA is expected around 2035. I think we still live by that time, in 9 years. So here, it shows the color lines, shows you the sensitivity curves of all these 4 future space-based gravitational interferometers, and the black lines are what our model predicts. So you see they intersect. So they are going to target the range of millihertz. Okay, so this means there is a chance to either either support or disfavor our model from this data. So this is a way how the theoretical models of primordial black hole production can be checked or falsified, approved, disapproved in the not so distant future. Not only our models, there are several models of this, but this is a way how this is likely to be going in the next 10, 15 years. Okay, so now I want to ask how much dark matter we can generate from our models. Yeah, this depends upon the parameters, which are not free, but we have some range of parameters. So what is remarkable here, the graph shows you on the one side what is not possible. So all colored regions are forbidden from different astronomical observations. This is 100% dark matter. This is 0% dark matter. What is remarkable about this background? Remarkable is the existence of the window between 10 to 17 to 10 to 24, where there are no observational constraints. This is called asteroid size window for primordial black hole dark matter, where primordial dark matter can be maybe 100%. And we did not put it in, yeah, I didn't assume it, but our models just inside this window. By fine-tuning parameters, one can get 100%. But it is fine-tuning. We don't like fine-tuning. But what is definitely robust from our model is that it is in the asteroid size window. We cannot get supermassive black hole. Sorry. We don't know how to get it. But our models belongs to this asteroid size window, and it seems to be very interesting. Good. So I think now I'm ready to conclude. Yeah. And also answer some questions from yesterday. So the whole approach which I advocating is based on gravitational origin of inflation, dark energy, dark matter. Okay. So it's possible to promote it to viable inflation, to very simple, efficient description of inflation, to efficient PBH production, and in principle checkable by induced gravity waves. Actually, I can tell you that we are doing it in the context of not gravity, but supergravity, because we also want a connection to the standard model. Why the naive connection to the standard model of elementary particles doesn't work? Yeah, I was talking about all this stuff completely disconnected from standard model. Standard model, you know, standard model is a quantum gauge field theory of elementary particles describing three interactions except gravity. It has a Higgs particle, which is a scalar. So of course, naive thinking would be, oh, you need a scalar for inflation, you have a Higgs, so why not Higgs cannot be a driver for inflation, yeah? I told you that it's naively it is impossible because just the bound on tensor to scalar ratio, if you take a high scale Higgs potential, which is lambda phi to the 4, lambda has to be 10 to minus 14, which is unacceptable. But there is a different reason, which is even more important. You know, in quantum field theory, you have to connect electroweak scale 100 GeV to the 10 to 13 GeV. You know, in quantum field theory, coupling constants are dependent upon the scale due to renormalization. If you increase, you can calculate how the lambdas, how the gauge coupling go with energies, and you can try to do it until the to much higher energies. Basically, standard model, two-loop renormalization group beta functions are known. So you can put it in and calculate. What happens with Higgs potential? Higgs potential, you know, is this famous double well potential, but in front of it, there is a lambda, okay, coupling constant, lambda. Higgs potential is lambda phi squared minus v squared squared. Yeah, there is a coupling constant in front of this double well potential. This lambda is running with the energies. You take standard model, can check how this lambda running. You'll be surprised. It is decreasing, and at 10 to 11 GeV, it becomes negative, which is a disaster. Negative lambda is destabilizes vacuum, and so on. Remember, I was telling you 100 times that inflationary scale 10 to 13, and lambda becomes negative at 10 to 11. So Higgs cannot be in Platon unless you add something. We say, oh, wait a minute, I go to the literature, I push ChatGPT, they say 1,000 papers about Higgs inflation. Well, they add extra stuff. They add extra stuff, like non-minimal coupling with gravity, then you can do whatever you, well, not whatever, but if you add, you can always change, twist anything. We are doing differently. We supersymmetrize. We supersymmetrize standard model to MSSM. In MSSM, lambda is never negative by supersymmetry, because in supersymmetry, lambda is related to the squares of gauge coupling constants. It's not arbitrary parameter. It is connected by SUSY to the gauge couplings, and it's never negative. So if in supersymmetric context, you can connect actually MSSM and also standard model with this stuff. But this is a separate lecture course, okay? And this is a very different story. I cannot cover it within 3 lectures even. And actually, this is a front page of current research, so, okay? How to make it. It's non-trivial. Good. So what else? What we found is PBH masses are in the asteroid size window. They can be dark matter. Actually, in supersymmetric context, it doesn't have to be 100% dark matter, because there is no reason to insist that dark matter is completely out of primordial black holes. For example, supersymmetry has its own natural candidate for dark matter, which is so-called LSP, lightest SUSY superpartner, which is stable, not neutral, and so on. So this brings more natural the context of composed dark matter having several components. If you want a detailed distribution of dark matter, this is depends upon the evolution of universe until now, which is not my business. I'm high energy physicist. This is to explain this particular pattern of dark matter distribution. One has to go into the detailed evolution of galaxies and clusters and so on. This is astrophysics. I'm not astrophysicist. Okay, and actually I don't know how to do that. I think they also don't know. But what is remarkable, I find that in terms of early universe, very high energy physics, this setup allows you to solve almost all cosmological problems at once. This is, I think, find it quite remarkable. Okay, and of course it is at the state of the art now. So my always intention was to connect something from the well-known stuff to state of the art. I hope in a small piece I at least give you some flavor of this. Okay, so this is a picture which I want to finish. It's not mine. It is from Plimak and Abrams. So they just demonstrates in one slide why black holes are so interesting and important area of study, because it connects micro with macro. Yeah, we don't know what quantum gravity is, but for quantum gravity we have almost no experimental input, observational input, but black holes can be a bridge which connect macro and micro, quantum and classical, and say primordial black holes we get are just here between asteroid and lunar size. Okay, but of course this is not a full story. It would be nice to get everything. Yeah, so this is I think can be exciting program for PhD students, for postdocs, for any researcher, and this is a front line of current research. So cosmology is not just something; it is combines everything. So I think it is very exciting, and what my purpose was to show you something very specific behind this picture. We don't know PBH exists or not. Yeah, even if they don't get 100% dark matter, if they exist, you have to throw away most of astrophysics textbooks because then you have to rewrite them. This is already enough, I think, to do this kind of research. Oh, 1 hour finished. Thank you.
Questions?
All right, thanks, Sergei. Regarding the nanograph signal, we know that the first order phase transition could also explain the nanograph signal.
Correct. This is PBH is not the only explanation.
Right. So then my question is, how could you pinpoint, like, hammer as this is a black hole, primordial black hole signal?
Good. I'm just talking what is possible. So even if, first of all, there is no proof, there is no nanograph results can be explained in various ways, because also the issue of PBH origin also can be explained in a variety of ways. So this means it is just a first manifestation, so to say, yeah, first check, but it is not a complete check. That's why even here, even though it is possible that the PBH explanation behind nanograph, there are other explanations, and at the moment there is no way to discriminate between them. However, in my business we have this, and again, if the laser will discover this phase, again it will be not a proof, but it will be supporting evidence for that. If you want ultimate proof of PBH, I said the most direct ultimate proof, discover any black holes with a mass less than 2 solar mass. This is a proof. But this is, I think, beyond current technology. The point is PBH can have any mass, and astrophysical black holes cannot. This is a crucial difference, at least immediately. But to make a full discrimination separation, of course, one needs more.
My point is, for instance, let's say even if we discover that we would discover primordial black holes with less than 1 solar mass, And as you pointed out, that you have a mass halo or mass function, that you might have a variety of black hole masses.
Yes.
Right. So it's really tricky to connect whatever you observed as primordial black hole signal. Let's say we did detect it.
Yeah.
But how are you going to tie that mass function or the population of primordial black holes to the dark matter density? Because how are you going to say, this is the population I saw in the galaxy, is the same population that's across all history of the universe, and explains the correct relative density?
Of course. So,
because we need primordial black holes not to be just present today, but as you said, from the very early on, the early universe for...
Yeah, evolution of universe can affect it, yeah. We are talking about of course, this is a very preliminary investigation. This means what we consider just as seeds of primordial black holes. Then there is a procedure, there is evolution of the universe, accretion, mergers. All this stuff I put away. Of course, it's important, and it's under discussion in all astrophysics seminars. But I addressed a much smaller question. What could be the masses of seeds of primordial black holes, and inflation, and our particular inflation gives mechanism and allows to estimate them. So what happens with them after? Absolutely legitimate questions, but I have no answer, because this answer should be addressed to astrophysicists, not to cosmologists, you know. We are talking about particular energies, about early universe, where I have expertise. I don't have expertise in evolution of galaxies, which is poses thousands of other questions. But this is, we should address it to astrophysicists. What I'm just telling you, the basics, yeah? Basics and what may happen, and it is specific enough, specific predictions. To check these predictions, I propose basic check. But it is not an ultimate check, of course. I'm just showing that it's possible.
More questions? So, yeah.
Okay, are these PBEs formed during inflation or after or even before inflation?
Again, sorry, I missed.
Are the PBEs created during inflation, after?
So
after
creation creates just a large perturbation. Then they evolve.
Okay.
So after inflation, they gravitationally collapse into black hole. Of course, after.
Okay.
But quickly prints, yeah. And then for the whole 13 billion years, there is an evolution of these seeds. And this is a very tricky question, how this evolution affected these seeds. This is, I cannot answer, but this is not question to me. Sorry. This is astrophysics, which is open area.
Just to understand this better. So they are formed after inflation.
After, but pretty soon.
Before matter and radiation decouple, or also?
Well, essentially during the, well, it is, I think I answered this question. Yeah, it is. Second inflation creates seeds. Yeah, but they have to gravitationally collapse. It goes after. Okay. So you can easily it just here. Put here asteroid mass. You get a time when they arise. Yeah, so it's definitely less than 1 second, because at 1 second you get already 10.5 solar mass. This is a tiny second. Okay. A tiny portion of a second.
Okay, yeah, that answers my question. Thanks.
Okay. So let me ask the last question. So the primordial black holes have been on the market for many years, many decades, and there are certainly estimates. I think until recently, at least, the majority thought that the abundance is not sufficient to be dark matter. So did something change, or does your model change something?
Unfortunately, Hawking is not with us, but Bernard Carr is still with us. So he starts his talks with showing the graph of sociology, how many papers devoted to black holes, yeah? So there was a few papers, 67, then 40 years, nothing, and then last year, thousands of paper, 2000, I guess, about primordial black holes. First of all, I think one reason for that is that people were quite disappointed by 25 years of search for dark matter particles, which did not, this is my feeling. Second feeling, this is a new type of research. You have gravity astronomy coming. LIGO was the second boost, because now there is no question, black holes exist, yeah? So, and if they could be dark matter, great. This would be a viable alternative, yeah? But then the question comes, whether it is 100% or less, because I showed you the Press-Schechter equations. These equations can be easily criticized. I mean, this stuff. This is a standard approach. It's called a Press-Schechter for calculating omega in astrophysics. But the problem is that it can be criticized severely because it assumes Gaussianity, for example. And there is also no reason why it should be 100% dark matter, yeah, by primordials. So now it is an active area of research. And most recent opinion, if you go to the conferences, for example, there are many conferences devoted specifically to PBH, they say it's rather unlikely to have 100% primordial black holes dark matter. Because you have it also, you can see it here, it requires rather significant fine-tuning, and also ignoring several things which can easily change significantly this number, not just by some small portion, but radically. So this is what current research point out, that it may be just about maximum 10%. But again, even if it exists, I said it's a revolution, even if it is 1%. Okay, so the current literature tends toward composite dark matter. And I said supergravity is a good thing about that, because there are two natural sources of dark matter. If you do Stravinsky supergravity and generalize this, it's what we are doing. Actually, this is, I did it with my students. What we are really doing is supergravity stuff with MSSM. Then you have another, supersymmetry has a natural candidate for dark matter, it's called LSP. It is either neutralino or gravitino. And then combining these two sources gives you much more, how to say, flexible picture about dark matter. So 100% dark matter is unlikely, I guess. But this is, it may be possible, but simply seems to be unlikely. Okay. There is another issue which was recently discussed in the conferences, that this band 10 to 15 gram relies on Hawking formula. But Hawking formula was derived semi-classically, so it cannot be used for very high temperatures and very small masses. You have to consider some back reaction effect, like a memory back reaction and so on. So actually this opens the window even smaller PBH masses, like 10 to 9 gram. So then, well, but 10 to 9 gram, I think it will be impossible to detect within the next 50 years. So we are now in the front line of research. I cannot make a definite statement anymore, okay? But young people, welcome to contribute, okay? This, we are reached the point where which are all debatable. This is a front line of research. Okay, thank you very much for your attention. So I invite you to the February 20. There will be no math, but it will be in a more general context, including art and so on.